right, so in the first part of section 6.1, we looked at how to convert between degrees and radians, talked about some different properties and how to classify angles, how to draw angles, and that kind of stuff. First thing we're going to look at in this section is what's called arc length. Okay. The idea of arc length is it measures basically something like this. If you have a circle, actually, you know what? I'm not even going to draw axes. If you just have a circle and you draw an angle inside that circle, the two sides of the angle are going to hit the edge of the circle somewhere. If you connect the dots between where those 2 points are, that part in blue is called an arc. That's what we're measuring the length of. Okay? What do you think would change the size of this arc in blue? There's actually two things I could change. Yeah?
If it goes counterclockwise, if it moves counterclockwise.
So what's something that I could change there that would change the length of the arc? I could change the something. Yeah?
You could change how large the circle is.
I could change how large the circle is, yes. Right? If I took that same exact circle, photocopied it, made it 150% bigger, yes, it would change the size of the arc. And there's something else I could change without changing the size of the circle. What else could I change? I could change the size of the angle. Yep. So there are two things that affect that arc in blue. And when we come up with the formula, it's going to have those two things in it. The size of the circle and the size of the angle. All right, so the first thing is that if you draw an angle and an arc in that circle, they are what we call directly proportional. So let me draw another picture, but let me do it a little differently. Let's say we had, I can do it that way. Let's say we had this picture. Here's an angle inside the circle. How big is the angle that I just drew?
90 degrees.
It's 90 degrees. And now the arc, that's in green. How much of the circle does the arc take up?
A quarter.
A quarter. So the arc is 1/4 of the circle. If those two things are directly proportional, which I said they were, that means as you change one, the other one changes exactly the same way. So if we double the size of the angle, it would be 180. What should be the size of the arc in that case? It should be half the circle. Let's draw it and see if that actually works. If it works, then it means they are directly proportional. So here's my angle doubled. That is a 180 degree angle. So let's write that down. And the arc is, let's look at the arc now. Arc goes from there to there. How much of the circle does that arc actually take up? Yeah, it does. It does take up half the circle. So what I'm trying to show you there is whatever you do to the angle, the exact same thing happens to the arc. If you made the angle 1/3 as big, what do you think would happen to the arc? It would be 1/3 as big. Yep. If you make the angle 5 times as big, you make the arc 5 times as big. Yep. They go together. And because they go together like that, that's called directly proportional, and that allows us to create a proportion in our circle. Okay, so we're going to set up a proportion, and that's going to give me the arc length formula. Okay, so let's start with that. To set up a proportion, you need 4 things: a fraction on the left and a fraction on the right. So I've drawn a circle with 4 things: an arc and an angle, another arc, and another angle. So those are my 4 things circled in green. So what I want to do is set up a proportion with those four things. And I can do this because we know that as one changes, the other one changes exactly the same way. So here's going to be our proportion. We're going to fill in those four things. There's a lot of ways you can set up the proportion. The only rule is that however you do it on the left, you have to do it the same way on the right. So can someone pick two of those things in green to put on the left? Yep.
Put one of the S's on.
So which one?
S.
S, okay, over.
I forgot what it's called. The 0.
Yep, what's that called?
Theta.
Theta. That's fine. Okay, so you pick two of them. Now you need to set up the right side exactly the same way. What would have to go on top on the right?
S1.
S1. And the bottom?
Theta 1.
Theta 1. Yep. Okay. Any question on that? All right, you can't really go wrong as long as whatever two you put on the left, just set it up the same way for those two on the right. Don't put like the arc in the top here and then the arc in the bottom there. Can't do that. Okay, so that we can do because they're directly proportional. Now, a proportion isn't really helpful unless you know part of it. Like let's say you were trying to convert from feet to inches. You could try to set up a proportion. You have to put feet in the same spot. And you have to put inches in the same spot. But without knowing something, that's useless. What you have to do is fill in a fact that you know is true on one side of the proportion. So what is a fact that is true about feet and inches?
1 foot equals 12 inches.
Yeah. Is that the only fact that's true about feet and inches? No. She could have said 2 and 24. That would have been fine. But the point is you need to plug in something that you already know is true on one side. How do we know that's true? Well, we memorize that from past. We have to do the same thing here. We have to fill in something that we know is true on one side. Right? And this is going to be something that I taught you yesterday. Let's suppose that theta 1 is 1 radian. If theta 1 is 1 radian, then it automatically makes this arc, S1, the same size as something else. That's going to be the fact that we know is true. Does anybody remember if this angle is 1 radian, then this arc is automatically the same length as what? So this is one of the first things we said when we looked at the definition of a radian yesterday. If that angle is 1 radian, then the length of this arc is the same as the radius. That's going to be the fact that we know is true. Okay? It's not as simple as 1 foot equals 12 inches, only because you maybe hadn't learned it till yesterday. But it is exactly the same idea. It's just a true fact. Is it the only true fact? No, there's other ones. But that is one. If that angle is 1 radian, then that arc is the same size as the radius. And the radius will be given to you in the problem. That's why that's important. Okay, so we're going to fill in our 1 foot equals 12 inches. We're going to fill in our true fact on the right-hand side. So now we have one side where we don't know anything, and we have another side where that is like my 1 foot equals 12 inches, what I just put the box around. That's our true fact. Now, does anybody remember how you solve a proportion? Yep, you cross multiply. What is S times 1? S. And what about R times theta? just r theta. And that is the formula for arc length. S equals r theta. So it comes from that proportion. The S is the length of the arc. R is the radius. And theta is the angle. So remember I told you the arc length would depend on two things? I told you it would depend on how big of a circle you draw, and it would depend on how big of an angle you draw. Well, r is how big the circle is. Theta is how big the angle is. Now, what does it say about the angle? Has to be in radians. So if you have a problem and it asks you to convert, or it asks you to do something with that formula, and you have an angle that's not in radians, you have to convert to radians first. Okay. The way this formula is going to work, you're always going to be given 2 out of 3 of the variables, and you'll solve for the one that you don't know. So let's try an example. So this says find the length of the arc. So first sentence, they're telling you what you need to do right away. Find the length of the arc. The circle has a radius of 2 inches. And we have an angle of pi over 4. Now generally, you're not going to get a picture and a word description. You don't need both. Okay, but for this one, I gave you both so you can kind of see and read what we're doing. So first thing is to figure out, or remember, your formula. What is the formula that we're going to need that would have a spot for all the pieces of information in this problem? Yep, it's S equals r theta. Okay, what are they asking me to find?
The arc length.
They're asking me to find the arc length. Which variable there represents arc length?
S.
S. So we're going to leave that as S. Since we don't know S, we need to know everything else. Okay. What do they give me for the radius?
2.
Radius is 2. And what do they give me for an angle?
Pi over 4.
They give me pi over 4. And I know pi over 4 is in radians because there's no degree symbol on it, so I can use it just the way it is. Okay, so multiply that together. 2 pi divided by 4. And what does that reduce to?
Pi over 2.
Reduces to pi over 2. And remind me again, what did we just find?
Arc length.
The arc length. Okay, so we found something that is a length. There does need to be a label on that. What label should I put on that since it's a length? In this particular problem, yes. Lengths were measured in inches, so it's about 1.57 inches. That's it. Any question on how we got that? Let's try another one. This time it says find the radius of the circle. Okay, so you're finding something different. The arc length is 3 pi feet. And the angle is 60 degrees. So first, what's the formula that would have a spot for all of those things?
S equals r theta.
Yep, it's going to be S equals r theta. Let's start with S. Did they give me S?
Yes.
Yeah, what did they give me this time?
3 pi.
3 pi. Okay. Did they give me R? No, that's the question. Find the radius. Okay, did they give me an angle?
Yes.
Did they give me theta?
No.
No. They did give me an angle, but that is not what you plug in for theta. What do I have to do to the 60 degrees? Convert it to radians. So we multiply by pi and divide by 180. And what does 60 pi over 180 reduce to?
And then pi over
pi over 3. Okay. So now we've got to get r by itself. So we have a fraction next to the variable. We can move the pi and the 3 at the same time. Does anybody remember what you could multiply both sides by, and it would get rid of the pi and the 3 at the same time? Yep, the reciprocal. So multiply by 3 over pi. Multiply by 3 over pi. What's going to cancel on the right?
Or well, the pi.
The pi's
Three.
and the 3's. And what are you left with?
R.
So you have r. And what are we going to get on the left?
1. 9. Oh, 9.
9, because the pi's are gone.
9.
And remember, that's a radius.
Oh.
So what should be our unit on that?
Feet.
Feet. Radius, again, that's another example of a length. So that's 9 feet. So that's the idea of the arc length formula. They give you two variables, and you solve for the one you don't know. Any questions on that? All right, so that's the first topic. So it's 3 topics. It's 1. Second topic, angular velocity. So well, velocity basically is like speed, right? It measures how fast something is going. Angular, that measures how fast something is going by using a unit that measures angles. Degrees, radians, revolutions. You use revolutions to measure angles. We did a few of those in the homework, like a quarter revolution, and we had to convert to degrees. We don't use revolutions as much to describe an angle. We normally would say degrees or radians, but you can. So angular velocity is used to measure the speed of something that we could measure using an angle. What can we measure using an angle? Something spinning, right? Moving on a circle. So angular velocity measures the speed of something that's rotating or spinning. So why don't we just use linear velocity? Why do we have to, why measure something in like how many radians per second or how many revolutions per minute it's making? Why not just use like miles per hour or feet per second or kilometers per hour? Well, if you use linear speed to describe something spinning, something kind of weird can happen. Look at these 3 dots on that disk. Okay, there's a black one in the middle, a red one, and then a black one that's on the outer edge. Does anyone remember the formula that connects distance, rate, and time? Distance equals r, yep.
Times
Distance equals r times, yep.
T.
T, yeah. That's the distance formula. So now, let's apply that to something I'm going to do right here. I'm going to take that disk, and I want you to watch as I spin it one time. Watch all 3 dots. Which dot traveled the furthest?
The outside.
The outside one. Okay, so the outside one, everybody agrees that one traveled the furthest. Okay. Now, how much time does it take for each one of these dots to complete their path of travel? Like if you compare the time it takes for that one to travel, and the outer one to travel, how do the times compare? All the times are the same. But this dot traveled the farthest. So what would that mean? If this dot traveled farther in the same amount of time as everything else,
Going faster.
it has to be going faster. And in fact, every single point on this edge of that disk is traveling at a different linear speed. Okay? Because they're all traveling different amounts of rotation, but they're all doing it in the same time. Right? That makes describing the speed of this spinning very complicated. Like where you describe the speed. For somebody standing right in the middle, basically you'd say the speed is 0. there's no travel at all. So does that mean it's not moving? Well, yeah, if you were in the middle, you wouldn't be moving, you'd just be staying in place. Right? But if you're on the outer edge, you'd be traveling the fastest because you're making the biggest circle out of everybody. So that's why describing something spinning with linear speed doesn't work. We don't describe the speed of something spinning as how far a point moves. Well, how we describe it is how many revolutions those dots make. That way, they're all traveling at the same number of revolutions per minute. Even though the size of the revolution is different, yes, there's no question, the size is different. But each one of those 3 dots is all traveling at maybe 1 revolution in, maybe it took me like 5 seconds to do that. So the speed is 1 revolution per 5 seconds. That's why we use revolutions to describe something spinning. Any question on that? Okay. So the default unit that we're always going to use for angular speed is radians. There are 3: degrees, radians, and revolutions. All 3 of those measure something spinning. If they don't tell you what unit to use on the test, in the homework, the unit they want is radians. What's the standard time unit? There isn't one. Seconds, minutes, hours, days, years. I would just use whatever time unit they use in the problem. Now, if you compare that to linear speed doesn't use angles, it doesn't use radians, degrees, or revolutions to measure how far you go. Distance in a linear way is measured in like feet, inches, miles, centimeters, millimeters, kilometers, okay, things like that. So it still could share the same kind of time unit, but it's a very different way of measuring distance. One way uses revolutions, radians, or degrees. The other way uses like feet, inches, miles, something like that. And what we're going to do is convert between the 2. And the way that we're going to do it is to use dimensional analysis, which basically means you're going to look at fractions and we're going to cancel units out. It's kind of like how I told you to convert between degrees and radians. If you have 80 degrees, we know degrees goes in the bottom if we're trying to convert to radians because it's in the top on the other one. So we just have to do the same idea, cancel out our units. And if you want to kind of get like a mental picture of what would happen trying to convert angular to linear speed, the idea would be if you had a tire spinning on a machine, right, rotating. Maybe it's rotating like 2,000 times a minute, and it's balancing a tire. And all of a sudden, that tire fell off the machine, and it hit the ground, right? What's going to happen? All of a sudden, assuming it doesn't fall over, the second it hits the ground, it's going to take off straight, right? It's just going to go in whatever direction it was spinning. That's an example of going from angular to linear speed instantly. Something spinning, falls off the machine, hits the ground, and now it starts rolling on the ground in a direction. Right? That's angular to linear. Another example would be if you had like a rope, right? like a lasso or something. If you're spinning it, okay, it's going around your head, maybe you're rotating it at like 2 revolutions a minute or 2 revolutions a second. If all of a sudden you let that rope go, it's going to go in a straight line. It's going to take off. You instantly converted angular speed, something rotating, into linear speed, the rope going straight out in a direction. All right. So that's the idea of what we're going to try to do. But we'll build up to that. Okay. We're going to start out with a very, very just basic conversion, just converting days to minutes, just to practice units. Okay. That's not even a speed. That's just a time. So let's say we have 3 days. To convert that to minutes, we're going to go one step at a time. We're going to go from days down to the next smaller unit. What's the next unit? What's the next time unit that's down from a day, getting towards minutes? Yep.
Hours.
Hours. We want days to cancel out because ultimately we want to get minutes. Where would days go in this second fraction? It would have to go in the bottom. Yep. So I'm going to put days in the bottom. And what unit would go in the top?
Hours.
Hours. Now you need to fill in the conversion. I need a fact that's true between hours and days. Any fact.
24 hours is in one day.
There are 24 hours in one day. Okay, that's dimensional analysis. All right. Now we want to get rid of hours. So where would hours go in the next fraction? Would go in the bottom. We're going to try to convert hours into minutes. Hours is now gone. Now I need a true fact between hours and minutes.
60 minutes is an hour.
Yep, any fact will work as long as it's true. That's the simplest one, though. 60 minutes is 1 hour. Now, what's the only unit you haven't crossed out? Minutes. So multiply straight across. 3 times 24 times 60. And in this case, it's just divided by 1, so you don't need the 1. It's 4,320 minutes. Any question on that one? All right. So now let's try a rate. So not only is there going to be a time component, this number is also going to have a distance component. What does that mean? Like if you read that.
It's traveling 50 feet per second.
Right, this object is moving 50 feet across the ground in every second. So that's 50 feet in 1 second. Seems pretty fast. We're going to convert that to miles per hour. So there's 2 separate problems we're doing here. We're trying to change feet to miles, and we're trying to change seconds to hours. Let's deal with the time unit first. What's the next unit up from seconds to get to hours? Minutes. We're trying to get rid of seconds. So where would seconds go?
The numerator.
In the top. And where would hours go? Hours would go in the bottom. Okay, so we fixed that. So now it's minutes. What's a fact that connects seconds and minutes?
60 seconds in a minute.
60 seconds in 1 minute. Now we have a speed of feet per minute. We're trying to get to hours. Okay, so minutes needs to disappear. Where would minutes go?
The top.
So minutes in the top. What unit goes in the bottom? Hours. And what's a fact that connects minutes and hours?
60 minutes in an hour.
There are 60 minutes in an hour. Okay, now we have a speed in feet per hour. We want miles per hour. So the next step is to get rid of feet. Look where feet is now. Where would feet have to go?
The bottom.
Feet in the bottom. What in the top? I think we should know how many feet are in a mile. That should be a fact we could jump right to. So, how many feet in 1 mile?
Wait.
Does anyone know?
5,280.
5,280. Yep.
How do you know the topic?
So 5,280 feet in 1 mile. Okay. And you don't really have to go to yards in that case. If you knew how many yards were in a mile and you knew how many feet were in a yard, then okay, you could. And now look at the unit you're left with. Miles in the top, hours in the bottom. So that's going to be a speed in miles per hour. So multiply everything in the top. 50 times 60 and 60 is 3,600. divide by 5,280. So if an object is traveling at 50 feet per second, that's about 34.09 miles per hour. Miles per hour. There are two units that sometimes we see a three-letter abbreviation. MPH, if you ever see that in this class, it will stand for miles per hour. And RPMs, that would stand for revolutions per minute. Other than that, I always try to use unit/unit, so you clearly know what the units are. Okay. All right. So that was a linear speed to a linear speed. Let's try angular to angular. We're traveling 200 radians in a second. What's the time unit that they want?
Minutes.
Minutes. So how do I fix that so I can at least get rid of seconds?
Seconds on the top and minutes on the bottom.
Yep, and what would be your whole conversion?
60 seconds equals 1 minute.
60 seconds in 1 minute. Okay, time is taken care of. Next conversion. We're trying to get rid of what and end up with what?
Get rid of rad and get rad.
Right, we want to get rid of radians and we want revolutions. What's the connection between radians and revolutions?
360.
Well, revolution is 2 pi.
One revolution, bless you, is 2 pi radians. And now when you multiply that out, you have your answer. So 200 times 60 divided by 2 pi. That's 1,909.86. 1,909.86 revolutions per minute. That is when you might see RPM as the label. Okay. Any question on that one? All right. So, last one. Okay. We're just going to focus on part B, which is going to be the only part. Says a wheel that's 18 inches is rotating at 1,850 revolutions per minute. So imagine that wheel spinning on a machine, and it falls off the machine. I want to know if it falls off, how fast is it going to be coming at you? Okay, so let's start with the speed that they give us, 1,850 revolutions per minute. What do they want for a time unit?
Seconds.
They want seconds, so we can fix that first. How would I fix that so I have seconds? Minutes over seconds. 60 seconds in a minute. Okay, so now we have revolutions per second. We have the right time, but we don't have the right distance. We don't want to measure it as a revolution. We want to measure it as a foot. So just thinking about the units, where would revolutions go? Right, we're trying to get rid of that. And what unit are we trying to introduce? Feet. So now we have to figure out this fact. How many feet in a revolution? How many feet in a revolution?
1.5.
Maybe. Could be.
Because
Yeah,
it's
And
depends. How come?
Size of the revolution.
Right. Depends on the size of the revolution. So a revolution is a circle. Well, how big of a circle are you making? We're talking about a revolution around the sun. Like that big of a revolution?
So do we use the radius?
Yeah, and we've got to use the radius somehow to figure something out.
Doesn't it tell you?
Yeah, it was
Oh, it
18
tells you.
inches.
So it tells us that we have a wheel, and that is 18 inches. Well, first of all, they want feet, so we should fix the 18 right now. How many feet is 18 inches?
So 1.5.
It's 1.5 feet. Okay, so 18 inches you divide by 12, that'll change inches to feet. So we got 1.5 feet. One revolution, like if this wheel was to roll on the ground, like say I mark that spot, and I roll this wheel one time until that spot comes back on the ground again, and I measure that distance that the wheel rolled. That is something about the wheel. It's the what of the wheel? It's the circumference, yeah, the perimeter. Yep. So if we can figure out the circumference of that wheel, that is how long one revolution is. Imagine like this was like a loop of wire, and you cut it, and then you straightened it out. If you could measure that, that's how far the wheel would roll in one revolution. So what's the formula for circumference? It's 2 pi r. And what is our radius in feet?
1.5.
1.5. What's 2 pi times 1.5 as a multiple of pi?
Oh, that's 360.
Well, we're going to leave it as a multiple of pi.
Yeah.
3 pi.
3 pi, yes. That is the circumference of that wheel. 3 pi feet. Circumference is the revolution. So there are 3 pi feet every time you go around that circle one time. So that conversion is not a standard conversion you can memorize. You have to figure that one out based on the radius they give you in the problem. It's not like asking how many seconds are in a minute. That never changes. But how many feet are in a revolution? That changes every time. All right, now let's see what we get. So 1850 times 3 times pi. That's everything in the top. And then divided by 160 and 1. So just divided by 60. So that's 290.6 feet per second. So if you think about like a length of a football field, that's 300 feet. That's almost the length of a football field in a second. So that's probably pretty fast. So this conversion right here, that was the key that helped us go from angular to linear. Any question on that one? Okay. So that's the second topic, angular velocity. Last topic. So this is the last topic for the week, the unit circle trig. We'll see what we get through today, and then the rest will be tomorrow. So unit circle trig, different section than angular velocity. Okay. So what is unit circle trig? So the idea of unit circle trig is that you can draw a circle with an XY axis in the center. And then on that circle, I can make an angle. Somebody give me an angle.
50 degrees.
50 degrees. Okay. So 50 degrees, the initial side would be there. and maybe the terminal side would be somewhere up there. The point is that green dot. That's the most important thing in that picture. That green dot has an x value and it has a y value. It has an amount, like if you think of this as the origin, you have to go over and then you have to go up to get to that green dot. The point of unit circle trig is figuring out what that coordinate is. 50 is not an angle we would do on the unit circle. But the concept is still the same. For the angle that you draw, your terminal side is going to hit the circle, and you need to find the location of where it hits. What we do with that location, well, I'll show you. But that's the goal. Find the location of that point. So unit circle trig is all about a coordinate. That's kind of the fundamental thing. All right, so the idea, circle. Just reword that a little bit. So for certain angles, I'll tell you what kind of angles in a minute. So for certain angles, generally we're going to stick with 30s and 45s. 50 is not a multiple of either one of those. So 50 is not one we would do. But anything that's a multiple of 30 or 45, we can draw them in a unit circle and find the coordinate of where the terminal side hits the circle. Once you find that coordinate, you're going to have two numbers. Right? You're going to have an x, and you're going to have a y. Those x and y values are going to allow us to find the 6 trig functions of our angle. I'm just going to word it like that. So those x and y values allow us to find the 6 trig functions. I'm going to add in the word functions. Of the angle. So I'm going to talk about what the 6 trig functions are. There are buttons for them on the calculator. You might have seen them, like sine, cosine, tangent. Those are 3 trig functions. Secant, cosecant, and cotangent are 3 others. And there's more than one way to figure out what those are. The way that I'm specifically showing you is going to be called unit circle trig. So let's look at some certain angles. Let's look at some ones that are easy to do. 90, 180, 270, and 360. Okay, those are easy angles. And they are multiples of, actually they're multiples of both 30 and 45. Let's start with a 90. There's your initial. There's your terminal. When you draw a 90-degree angle, the point where the terminal side hits the circle is at the very top. Now, it's in the title of this section. What kind of circle is that?
Unit circle?
It's a unit circle. What does that mean about the size of that circle?
It's a specific unit.
No, it doesn't have a specific unit. It has a specific size. Anyone have a guess how big a unit circle is?
1 unit.
1 unit. What is 1 unit about the circle? Like the circumference is 1 unit?
The radius?
The radius, yes. So a unit circle is just a circle where the radius is equal to 1. So if that's the origin, or I just put the black dot, does anybody have a guess what the coordinate would be for 90 degrees? 0, 1. Yep. The x value is 0 and the y value is 1. How about if I drew that angle? How big is that angle in red?
180.
That's a 180. And does anyone have a guess what that coordinate would be? Negative 1, 0. How about if that was my initial and that was my terminal, going like that? How big is that angle in blue?
Negative 1.
How big in degrees?
Oh, 1.
0, negative 1.
So first in
It's
degrees,
270 degrees.
270 degrees. And the location of it?
0, negative 1.
0, negative 1. And I could do one more over here. This would be where the initial side and the terminal side are exactly the same. It's a 0 degree angle. What would be the coordinates for 0 degrees? 1, 0. Yep. So those 4 angles are what we call the quadrantal angles. And those are the coordinates for them. I say that right here. So quadrantal angles are 0, 90, 180, and 270. They are the easiest coordinates to find on the circle. They all have a 0, a 1, or a negative 1. They all have a 0. It's either a 1 or a negative 1 with it. So any question on how we got those 4 coordinates? Right. So like for 90 degrees, what's the x value? 0. And what's the y value? 1. Knowing that the x value is 0 and the y value is 1 would help us to figure out all the trig functions of 90 degrees. So how do you do it? Well, depending on which trig function you want to know, depends on which will control which part of the coordinate you need to use. If you are trying to find the sine of 90 degrees, once you know the coordinate, the answer is the y value. You actually don't need the x per sine. If you want to find the cosine of 90 degrees, once you know the coordinate, the answer is the x value. If you want the tangent of 90 degrees, you need to take the coordinate and divide the y value by the x value. All trig functions have a 3-letter abbreviation. And when I write them down from now on, I'm always going to use what's in parentheses. Okay. Those are our first 3 trig functions. Okay. The next 3 on the other side have a connection to the first 3 we wrote. Look at the answer here and the answer here. How do those 2 answers compare to each other?
The second answer is being divided by the first answer.
Okay, and what do we? There's a word for that in math. The second answer is the
Reciprocal.
reciprocal. Exactly. All the answers that I write down on the right are going to be the reciprocal of the one on the left. So let me give you the names of them first. Cosecant, secant, and cotangent. Now, if what I said is true, the answer under the box is going to be the reciprocal of the other answer in the same row. So what do you think the secant is?
1 over x.
It's 1 over x. And the cotangent? X over Y. Yep. So those are our 6 trig functions along with their definitions. So the idea is I give you a coordinate or you find it, and then you plug the coordinate in to whatever formula I ask you for. If I ask you for the cosine, you give me the x value as the answer. If I ask you for the tangent of something, you have to find the coordinate first, and then take the y and the x and divide them. So definitely I would put those on a reference sheet. I think I already gave you that. Okay, so the 2 steps for doing unit circle trig. So I'll give you these 2 steps. We'll do one or maybe 2 examples, and then we'll stop there. So the first step to doing unit circle trig is you need a coordinate. If they give you the coordinate, great. Step 1's already done for you. If they don't give you the coordinate, then you need to do step 1. You need to figure it out. Right now, there's only 4 coordinates I've shown you how to find. 0, 90, 180, 270. I would not give you an angle at this point and have you find the coordinate if it wasn't one of the 4 that I just said. Okay, so use the coordinate that they give you. And then we're going to plug that coordinate into these formulas. On the test, I would ask you specifically for one of the 6. When we do the practice problem next, we're going to do all 6. Okay, so here's the first one. Am I giving you a coordinate, or do you have to find it? I'm giving it to you. Now, this coordinate does represent an angle, and you should know the angle, but you don't need to. What angle is that the coordinate for?
90.
90, that is true, yes. Do you need to know it's 90? Absolutely not. All you need to know is an x value and a y value, and that's it. Does everybody have the left side? I just want to delete that so I can bring the formulas back next to it. Okay, so let's start with the sine. We're going to find the sine of the angle, and let's pretend we don't know it's 90. Right? We know that it represents some angle. That is the location of something. Okay. Who cares what it is? What's the definition for sine? Sine is y. And what's the y value in that coordinate? 1. So whatever angle that represents, the sine of that angle is 1. Let's find the cosine of that angle. What's the definition for cosine?
X.
X. What's the x value in the location they gave me?
0.
So cosine is 0. Okay. Tangent. What's the definition of tangent?
Y over X.
Y divided by x. What's my y value?
1.
1. My x value?
0.
What's 1 divided by 0?
0.
1. It's not possible.
Right. You can't divide by 0. So that is undefined. Can't divide by 0. All right. Now, once we get the 3 on the left, what did we say the connection is between the 3 on the left and the 3 on the right? They're reciprocal. All you have to do is flip them. So the cosecant is this answer flipped. What do you get if you flip the number 1?
Isn't it just 1 over 1?
Right. Well, what is that as a fraction right now?
1 over 1.
It's 1 over 1. And if you flip it,
Just 1 over
it still is 1 over 1. Yeah. All right. The secant. How would you write 0 as a fraction?
1 over 0
Okay, so we're taking 0 over 1 and we're flipping it.
Undefined.
Undefined. So if we flip 0, we get undefined. If we flip undefined, we would get
0.
0. Yep. Okay. Any question on that? Well, we'll do some more tomorrow. All right. So let's see what we got. We were just about there. So page 324, that's the angular velocity. And then, all right, 1, 5, yeah, 1, 5, and 8. Let's just do those. So they're asking you in the book to find the coordinate. So for example, this isn't the exact one in the book, but let's say you had something like pi. Pi is what in degrees? It's 180. What's the coordinate for 180?
-1, 0.
-1, 0. So in the book, that's what they have you do for 1, 5, and 8. Figure out the coordinate. I want you to go one step further and take that coordinate and now find the 6 trig functions, just like I did in the last question we went over. Okay. So find the coordinate and find the 6 trig functions. So you should have 18 answers in your homework. 3 problems, 6 answers each. Right, and then page 324, that's angular velocity. We'll go over that separately.